Alrighty, thank you all for joining me. My name is Anthony Lima. This is a project that I've been working on with Dr. Suzanne Bricker of NCOS and Lily Walker. I'm a PhD student at Texas A&M University, Heart Research Center, Heart Research Institute. I'm going to be talking a little bit today about where oysters fit in with Texas aquaculture. Texas has only recently allowed oysters in maybe the past 2 years or so as an endeavor here. So it presents some unique circumstances for Texas and unique opportunities to be able to see how oysters can interact with our environments here. Okay, a little bit about the overall range of oysters. Here in Texas, you can see from this graph on the left, one of the issues that we see is we do not see consistent ability to farm, to capture wild stock. So because we have these huge rises and falls, it becomes kind of a tricky industry for those taking from the natural stock, as well as kind of creates a situation in which Texas is dependent on outside states to produce something that we should be able to produce here locally. On the right, we can see, should be a red circle, there we go. Mollusk growth as a division of aquaculture has been by far the fastest and most consistent growing for about 20 years. And with more states kind of not only oyster aquaculture, but adopting other kinds of shellfish practices and seeing how we can mitigate things like nitrogen pollution, this is expected to go up. So the main reason we care about nitrogen is for eutrophication. So when nutrient-enriched water enters the waterways, you get a slew of different effects. As these algae populations grow, they can starve plants of light, so it kind of changes the ecosystem that should be there. As the algal populations explode, they remove other nutrients that are necessary for other types of wildlife that should be there. And when they die, decomposition removes O2 from the water. So on the right, you can see some of the big issues. We see changes in chlorophyll A, death of submerged aquatic vegetations, toxic algal blooms, depending on the variety of species, and low dissolved oxygen. For this research, we're looking at three main components. The first is assets. It's a model with a pressure state response framework. And what this does is, it's a model in which we're looking at is the ecosystem able to handle the pressure, and is it able to buffer the amount of nitrogen going in? From FARM, which is a farm aquaculture resource management model. This is predominantly used by commercial aquaculture managers to see to create estimations of how many oysters they should be able to get and which size and growth. And part of that is kind of some biogeophysical models as well. So that's where we know how much nitrogen is removed because it's going into tissue and shell content for the oysters. And the last major section of this is a cost analysis. So if we know that nitrogen is being removed, we'd like to say how much is that worth compared to a wastewater management treatment facility or some other type of nitrogen mitigation. This is a map of the site. This is Copano Bay, about 215 square kilometers. It's shallow and wind driven. It's only about 5 or 6 feet anywhere you head out there. And there's a couple important things when we're concerned with nitrogen and we're looking at a map like this. One, we're seeing influences, or I should say sources of fresh water, which we have with these three little blue bubbles. And that's important because that could be a source of where the nitrogen is being taken from. If it's being applied from fertilizer, water will come pick it up and it'll enter the bay that way. And another is the surrounding area. So as you can see from here, I don't know if you can see my pointer, but this is mostly agriculture land with not many people there. Okay, and this is where that type of information becomes important. So this is a USGS tool called Sparrow, spatially related regression on watershed attributes. So what this is doing is quantifying how much nitrogen is coming in based on the land around it, as well as saying what is the source of it. So I took San Diego only because it's a completely different place. And there's a couple important things as we see simply the amount. We see 800 kilograms of nitrogen per square kilometer from the San Diego Bay watershed on the left. And on the right, we can see only 175. But another important piece is that we see that this farm fertilizer, it's a much larger source than it is in San Diego Bay. And what this means is your treatment and mitigation plan is going to be different based on your source of nitrogen. If you cannot treat for an issue that doesn't exist, or you can, but you won't solve anything. Okay, so this is the results of assets modeling. And here we can see 3 different categories on the left with this index and grade. The first being influencing factors. And we see dilution potential and flushing potential as having a red score or a bad score. And what this means is from based on the geometry and the way the geography of the area, there's not a lot of water movement. It's a low amount of water and it's contained very steadily in that land, and it has kind of sporadic inputs. So these are things that kind of harm the susceptibility. Number 2, we see eutrophication condition. This is a little bit of I would say a data poor area within our modeling, only because it's not very well written about, but we do see some instances of dissolved oxygens and kind of higher chlorophyll A content than we would expect to see. And future outlook for this area, we don't really expect anything too big to be happening here. This would be if a city is booming or if there's a new industry or anything like that. This is probably going to remain agriculture land for many decades to come. So this is the results of that farm aquaculture resource modeling. So there's a lot to unpack here, so bear with me. Both of these models on the left, on the right, take the same inputs. And when I say same inputs, I mean farming and culture practice. These are both for 7-acre farms with mortality of 25% and roughly 250 individuals, oysters per square meter. So all of those are identical features. These are identical farms given in 2 very different scenarios, environmental scenarios. On the left is our 2014 year, which is a year with very high salinity, meaning that there was low rain that year. And what we can see with that red circle is that about 2,929 kilograms of nitrogen are removed by those oysters being there during this time frame. This is 7-month harvesting time. And at the end of this model, we see 88.3 tons of oysters are harvested at the end of this culture period. On the right, we see low salinity. So it's almost a little bit too high in one area and a little bit too low. We really have drastic conditions here in our Texas bays, and it can make, there is no normalization with the data. You never know what it's going to be 2 or 3 years from now. For our wet year, we can see that the amount of nitrogen removed is pretty much half. So we had about 3,000 kilograms on the left and about 1,500 on the right. So see a reduction of about 50%, meaning these oysters, despite being in the exact same area, because of these environmental conditions, have experienced much less growth and much less ability to survive. And whereas in our high salinity year, we had 88.3 tons of oysters ready to be harvested, which is fantastic for the growers. In 2010, none of them reached it within that 7-month cycle. So that is a little bit concerning and kind of leads to some doubt. Now, there's a couple things you can do to mitigate this. We could run the length of time for a little bit longer. You can put maybe 8 or 9 months within our modeling to see if that kind of sorts itself out, since we are also dictating mortality. But it's just as an example to see pretty much half the growth within that same amount of time it can be really drastic for growers if they, especially since this is new in the state, they have low predictability.
Anthony, you have about 2 minutes to wrap up.
Okay. So now we'd like to know, with those two numbers that we have, we'd like to know what is the value of the nitrogen that is removed from their growth. We have 3 different management strategies. We have wastewater treatment, urban BMPs, and agriculture BMPs. So within our area, we would expect agriculture BMPs, which handles more fertilizer management and cover crops. We also have an estimation of the cost to remove 1 kilogram of nitrogen. We can see some really low lows and really high highs from some of the ag BMPs. We see as low as $7. And that can be something as setting hay bales or redirecting water to go over a field before it gets to the bay, kind of some simple fixes. On our higher end, we see stormwater, and this usually has to do with buying land and creating facilities and, having needing to use engineering as well as having people there full time. These are also some estimations. So just the highest example for that 2014 year would be over $14 million if that amount of nitrogen was removed with a costly urban stormwater system. And when we had the lowest amount of nitrogen removed, going the cheapest way would be about $10,000 from these agriculture BMPs. So 2 very big differences based on what you need to facilitate, what area you're working in. If you can imagine buying cheap land in Texas or buying something in San Diego for wastewater treatment, be completely different. And just very shortly, I know I'm running out of time, but there is, I believe, 2 states that have a nutrient credit exchange system. So this would be a way to pay farmers for the amount of nitrogen removed from their oysters. So these types of things are still in their infancy, and it's a little bit almost like carbon capture and trading credits in those, an intersection of economics and environmental management, but some really interesting things happening there. And lastly, we know that some Texas bays are experiencing eutrophication. Oyster aquaculture can be good for economic growth and improve water quality. Bioextraction rate varies very much with seasonal conditions. And these models are used to find a way to support and sustain healthy ecological status for both humans and the environment. And I'd like to thank the partners you see here and NOAA CCME for their support with this. Ready. Thank you.
So we have a couple minutes for questions. Any questions for Anthony?
Just a very quick question. I'm sorry I missed the earlier part of your presentation. When you were giving the numbers in terms of like nitrogen removal with the oysters, were you like just using a marketable size oysters? Like it is just like based on yeah.
Sure,
I am
sure.
just wondering like what the value, like a general range you used. Yeah.
So that number was for the amount of nitrogen that is within that oyster after it reaches 2.5 inches, or roughly 7 months of culture practice. So that number, it's actually a very small amount. There's other pathways in which nitrogen are removed. So this is only taking almost a physical transport or harvest. So that's only within the oyster. There's other. Okay, I'll leave it there before we run out of too much time.
Right, thank you, thank you.
Yeah, I think
thank you.
That's all the time that we have. So thank Anthony again.
Thank you.